Okay, girls, this is another example with summation notation. This question is from your textbook. It's exercise 8.13. So this is an example, exercise 8.13, question 10. And you'll notice that we've got this summation notation over here on the left. So we've got, this is the symbol sigma, which means sum of. So we've got the sum of the terms from r equals 2 all the way up to, they don't need to put r equals n, but it's from r equals 2 up to r equals n for this function here, 3 to the power of r. So we're going to rewrite this. So we're trying to prove that the sum of 3 to the power of r, start with a starting value of r equals 2 all the way up to r equals n, is equal to this expression here on the right, 9 times 3 to the power of n minus 1 all over 2. Okay, now what we're going to do is rewrite out this left-hand side. So our first term starts with r is 2. So what we're trying to prove is that 3 squared plus. Our next term will be r3. It doesn't have to tell you what it jumps up by, but it's from r equals 2 all the way up to n. So then we'd have, 3 to the power of 2 because r is 2. Then we've got 3 to the power of, what would be the next thing after r is 2? 3 to the power of 3 plus 3 to the power of 4 plus all the way up to 3 to the power of, we start with r is 2. This sigma symbol, this is sigma, it means the sum of, up to 3 to the power of n. No, the last term is n. So we're starting with r equals 2 up to r equals n. So 3 squared plus 3 cubed plus all of those up to 3 to the power of n is equal to 9 times 3 to the power of n minus 1 over 2. So that's our first one today using summation notation. Okay? Whereas the others were just summation types. They gave you that second row. Okay? So let's start. Step 1. I'm just going to write for n equals 1. What have we got? Left-hand side is, oh no, it's not n is 1 this time, it's n is 2. Yes, our first term is 2. So for n is 2, left-hand side is 3 to the power of 2, which is 9. And the right-hand side, when you put n is 2, we get 9 times 3 to the power of 2 minus 1 over 2, which is 9 times 3 to the 2 minus 1. 3 to the power of 2 minus 1 is 3 to the power of 1. 3 minus 1 is 2 over 2, which is 9. Okay, that's step 1. Step 2, assume. Remember, it's assumed true for n equals k, so what are we just going to write? Assume that 3 squared plus 3 cubed plus 3 to the power of 4 plus 3 to the power of k. Assume true for n equals k. So therefore, we're going to assume that 3 squared plus 3 cubed plus 3 to the power of 4 all the way up to 3 to the power of k equals 9 times 3 to the power of k minus 1 over 2. Okay, everyone, pink is gone and it's a bit clearer now. So step 2, assuming true for n equals k. Step 3 is to prove that it's true for n equals k plus 1. That is, we're trying to prove that. What do I do? What do I write? All of them, and then, so we go 3 squared plus 3 cubed plus 3 to the power of 4 plus 3 to the power of k plus 3 to the power of k plus 1 equals what? 9 bracket 3. What do I do now? Replace the n with a k plus 1, but it becomes k plus 1 minus 1, which is k, I'm just going to write 3 to the k, minus 1 over 2. That's what we're trying to prove. I mean, if you want, you can write it out in 2 steps here and put that it's 3 to the, if you want, you can go k plus 1 minus 1, which is 9 times 3 to the k minus 1 on 2. So if you want to show that step of working where you're replacing the n with the k plus 1. Okay, so again, you know what to do? Start with that left-hand side, replace the bit up to 3 to the k with the assumption, and try and manipulate it so that you get that term on the right, that expression on the right-hand side. So we start with the left-hand side is 3 squared plus 3 cubed plus 3 to the power of 4 plus 3 to the power of k plus 3 to the power of k plus 1, which is equal to 9 times 3 to the k minus 1 over 2 plus that last bit, 3 to the k plus 1, using the assumption in step 2. Okay, look at what you're trying to get. Common denominator is a good idea. The other thing is, what does 3 to the k plus 1 means 3 to the k times 3. 3 to the k minus 1 means 3 to the k times 3 to the minus 1, or 3 to the k over 3. Okay, so there are a few things that you want to do. I'd probably be putting the 2. I think you need to put a 9. We need a 9 on 2 outside, actually. Anyway, let's just see when we change these into terms. Let's just see what we get. So what have we got? 9 lots of 3 to the k times, you're going to write it as 3 to the minus 1. We'll just write it as 3 to the minus 1. Take away 1. We okay with this? Over 2 plus, are we going common denominator? All right, so plus 2 lots over 2 of 3 to the k, So we're breaking up this 3 to the k minus 1, making it 3 to the k times 3 to the k minus 1. I just don't want to put fractions on fractions here because I don't have much room, okay? So remember, you'll be adding those, and k plus negative 1 is k minus 1. We'll fix up the 3 to the minus 1 thing later, okay? 3 to the k times 3. The reason we're going 2 over 2 is so that we've got a common denominator now of 2. So so what have we got? We've got 9 over 2, but there's no 9 for the first one, so I need to extend this line, okay? I've got, what can I do here? 3 to the negative 1 times, oh no, that's that take away 1, isn't it? I'll just write it out again. 3 to the k, actually no, I think I'll multiply by 9. Did anyone multiply by 9? All right, why don't we, actually, here we go, girls. What's 9 times this? This is 9 times 1/3. What is it? It's 3. So it's 3. I know you've got a 9 there, but let's worry about that later. So this becomes 9 times 3 to the negative 1 means 9 times 1/3, which is 3. So we've got 3 times 3 to the k. What do I write now? Remember, I'm expanding brackets here. I've done that times this, minus 9, good. Then what have I got? Plus, what's this? 6 times, see, 2 times 3 is 6. Lots of 3 to the k. 2, the reason I can put everything over 2 is because up here, the first expression has a denominator of 2, but the second one doesn't. So what I did, I put 2 on 2 in front of the second expression. Now everything has a denominator of 2. So I expanded. Just when you're doing this sort of expansion, just multiply this with the other number there, not with any powers. So 9 times a third is 3. 9 times minus 1, you get minus 9. And 2 times 3 is 6 times 3 to the k. What do we get here now, girls? You can see it's coming together. You've got 3 times 3 to the 3 lots of 3 to the k plus 6 lots of 3 to the k. So I can put those really in brackets, which is 9 lots of 3 to the k minus 9 over 2. See, it's 3 times 3 to the k, which is 3 lots of 3 to the k, plus 6 lots of 3 to the k. So therefore now what can we do? No, it's not minus 3. You've got a minus 9 here. So 3 lots of 3 to the k plus 6 lots of 3 to the k. Just think of the 3 to the k as an x or something. 3 lots of that plus 6 lots of that. Same thing. Gives you 9 lots of that thing. Well, here's the minus 9. So I've combined that and this together. And then I've got minus 9. Now, isn't 9 a common factor? 9 bracket 3 to the k minus 1 over 2, which equals right-hand side. And our conclusion, I'll write in the step 4. Therefore, if true, you start off with the assumption sort of thing. If true for n equals what? It's not n equals 1. 2. Then, no, for n equals k, thank you. If it's true for n equals k, then it is also true for n equals k plus 1. Since it is true for n equals 2, where'd you go? There. Weren't you at the... Since it is true for n equals 2, then it is also true for n equals 2 plus 1, which is 3, 3 plus 1, which is 4, and so on, for all n greater than or equal to 2. Here? Oh, if it's true for n is 2, see, if it's true for n is k, then we know it's definitely true for n is whatever k is plus 1. Now we've proven that it's true for n is 2. So therefore it's true for n is 2 plus 1, which is 3. And if it's true for 3, it's true for 3 plus 1, which is 4. No? I think I've got a little story thing on that. Something about birds. Okay? I'll just pause here. Summation type. Notice the notation on the left-hand side is different. This symbol is sigma, which means sum. So we're asking for the sum of all terms starting with r equals 1 all the way up to r is n for this particular expression here. So there are 2 types of summation types. They can be written out, like the series can be written out on the left, then equals that sum of things on the right, or it can be written this way, which is a condensed format. So what we'll do, we're going to substitute r is 1 into this expression to get our first term. So what do we get? So I'll just go that is, actually no. So we're trying to prove that, which is the same as proving the following. 2 times 1 is 2 minus 1 is 1. So we're trying to prove that 1 cubed plus, what do I substitute next for my value of r? This starts from r is 1 all the way up to r is n. The next one would be r is 2. When r is 2, we've got 4 minus 1 is 3, plus 3 cubed. Plus, when r is 3, we get 5 cubed. Now that's enough. Plus all the way up to, we're going all the way from r is 1 up to r is n. We'll replace the r now with a n, 2n minus 1 cubed. Now that's how you saw the questions yesterday. They started like this as opposed to that. That's the only difference that we're doing today. So 1 cubed plus 3 cubed plus 5 cubed all the way up to 2n minus 1 cubed is equal to n squared, 2n squared minus 1. That's what we're trying to prove. Okay, so step 1 for n is 1. What do we get? Left-hand side is 1 cubed, which is 1. Or you can put it in there, same thing. All right, and the right-hand side is 1 squared times 2 times 1 squared minus 1, which is 1 times 1, which is 1. So therefore, it is true for n equals 1. Step 2, assume true for n is k. That is, we are assuming that 1 cubed plus 3 cubed plus 5 cubed all the way up to what? 2k minus 1 cubed equals k squared 2k squared minus 1. Step 3. Yeah. Prove true for n equals k plus 1. That is, we are going to prove that 1 cubed plus 3 cubed plus 5 cubed plus
2k minus 1 cubed.
Now that's up to k. Now the next term will be 2 lots of k plus 1. And we've got to show that that is equal to, replacing now the k with k plus 1 squared times 2 bracket k plus 1 squared minus 1. We can either expand this if we want, or I suppose we can, which is k plus 1 squared. What would this be? Isn't this k squared plus 2k plus 1? What would it be? 2? I don't know. We might even leave it like that. Let's just see what we get. 2k squared plus 2 times 2k is 4k plus 2 times 1 is 2, but minus 1 is, I don't know. I'm not sure whether I'll do it like that or leave it like that. I've got it there in case. All right? That's the expansion of all of that. What I did, I got k squared plus 2k plus 1, then multiplied it by 2. You get 2 times 1 squared is 1, but then you subtract 1 to get the 1. Anyway, we'll see what we end up getting. Okay? Okay, left-hand side is equal to,
Isn't it k squared?
all right, what are we going to do? So we start with our left-hand side.
Sub in the assumption.
Good. We sub in our assumption.
Plus the 2.
So we get that it equals k squared bracket 2k squared minus 1 plus this other bit. And I'm going to let you have a fiddle now, girls. Using step 2 assumption, or assumption from step 2, it doesn't matter, even just using the assumption. I'll pause, you can have a go. We do not want to be doing polynomial factorizations, I tell you now. So, what we're going to do, what can we do? Should we make it k 2k cubed minus k? No. Because we're stuck here and we can't seem to find any factors, common factors or anything like that, what we're going to do, with our introduction statement for step 3, proving true for n is k plus 1, that is proving all of this equals that. And we did start to simplify it a little bit there. But if you've got a k squared here and a k squared here, you're going to end up with a k to the power of 4. Now we don't want, the only way you can factorize k to the power of 4s is with polynomial factorization. And that's a big long process and you don't want to be doing it in induction. So what we're going to do is come back over here to our that is prove the following. We're going to do the simplifying over here as opposed to the factorizing over there. Okay? So we've got 2k squared plus 4k cubed plus k squared plus 4k cubed plus 8k squared plus 2k, I hope I don't make a mistake, plus 2k squared plus 4k plus 1, which is, so I've just multiplied, we got 2k4 plus now the, 8k cubed plus now the k squareds, we've got k squared, 8k squared and 2k squared, 11k squared. The ordinary k's we've got 2k and 4k, which is 6k, and the numbers we've just got 1. So what I'm doing is trying to prove that my left-hand side equals all of that. So then just come back and expand your left-hand side. Now, I've got to show you how to expand these. Did I show you how it's 1, 3, 3, 1?
Wait, what?
The binomial theorem. You'll know how to do it soon once we've done binomial theorem, but we haven't done binomial theorem yet.
I thought it was just 2k minus.
All right, the way you expand something like the following, I'm just going to come off down the bottom here and show you a rule. A plus b cubed is So we're going to use that over here.
Isn't that minus?
There's no, oh, we've got a, no, there's no minus. No. Just before we expand this, a plus b cubed, you start off with the first and you cube the first term. Now, when you've got cubes, then it's, have you seen Pascal's triangle before? I'm showing you now. This is Pascal's triangle. Start with a 1 on top, then a 1, 2, 1. You know when you factorize a plus b squared, you get a squared plus 2ab plus b squared. The coefficients are 1, 2, 1. Then Pascal's triangle, the next row, you get 1 plus 2 is 3, 2 plus 1 is 3, then 1s. So if you're factorizing a plus b cubed, these are the coefficients of your factorization. We're doing this in our next topic, binomial theorem, all right? We just haven't done it yet. If you continue Pascal's triangle, what do you get? 1 plus 3 is 4, 3 plus 3 is 6. So if you factorize a plus b to the 4, these are the coefficients of your 5 terms. All right, so that's what Pascal's triangle can be used for. So if I'm factorizing a plus b cubed, my coefficients are 1, 3, 3, 1. Well, a cubed is 1, the next coefficient is 3. Now all you do, we started with the highest power of a, which here is a cubed, drop the power of a by 1 and you get a squared, and now introduce 1 power of b. Plus, the next coefficient is 3. Drop 1 power of a and you get a, and increase 1 power of b. And the last one's got a coefficient of 1. Drop 1 power of a and you get nothing, and you get a b cubed. That's how you expand a plus b all cubed. It's different to the factorization of a cubed plus b cubed. If I want to expand a plus b to the 4, I'm going to use this next row. All right, it's a4, highest power of a. Then the next coefficient is 4. Drop a power of a, introduce 1 power of b. Next coefficient, 6. And drop a power of a and increase 1b. Then the next coefficient is 4. Drop a power of a and introduce an extra b. And the last coefficient is 1. Drop an a, goes down to none, and you got b to the power of 4. If it's a minus, you alternate between pluses and minuses. The first one's plus, the second term's minus. We'll do that in the binomial. We do this in binomial theorem, all right? Now, so that way now we can expand this over here. All right, so we've got 2k4, because I've got to multiply it by the k squared there. 2k4 minus k squared plus. Now, according to this expansion, isn't it the first one's cubed plus 3 times the second one? You drop a power of 1, introduce 1 of the other b. Then we've got a 3 in front again. Just 2k, 1 squared, plus 1 cubed, which is 2k to the 4 minus k squared, plus 8k cubed, plus, now this is 3 times 4k squared, which is 12k squared. You square the 2k first, plus, this is just 6k, plus 1, which is 2k to the power of 4 plus 8k cubed. It's all looking good. Plus 6k plus 1, which equals the right-hand side. Okay, so that's all we had to do there. Girls, they're not going to make you do, you cannot do a, and you probably won't get one like this. They're not going to give you one where you just have to do this expansion. It's not really. So you won't be needing to factorize quartics polynomials with the power of 4. They're not going to expect that. So what you can do is just keep simplifying in that proof statement. Just keep simplifying that and coming up with something that's easier to obtain. Okay? And that should be it for today. So what you can do for homework, I've still got to do a divisibility type with, and that's your last, of course, your conclusion, okay? positive even integers n. Our first positive integer, even integer, our first positive even integer is 2. So we prove true for n is 2. Step 1. I'm just going to, you might have to watch this on video because I want to do it quickly. Prove true for n is 2. So we've got 2 times 2 plus 2 is, remember, 2 times 4, which is 8, which equals, which is divisible by 4. You can see it's divisible by 4 because it's 2 times 4, which is divisible. Remember, we're doing by 4, therefore true for n equals 2. So first we've proven that it's true for n is 2. So we put 2 up into here. 2 times 2 plus 2, which is 2 times 4 is 8, which is divisible by 4. Therefore true for n is 2. Step 2, assume true for n equals k. That is, we're going to assume that k bracket k plus 2 equals, how are we going to show that that's divisible by 4? Equals 4. Do you remember what we did with these? 4p. Where p is an integer. Step 3. Now, prove true. Girls, the next even integer is not going to be k plus 1. It's going to be k plus 2. So prove true for n equals k plus 2. Okay? That is, you're trying to prove that, here we go, replacing this, k plus 2 times k plus 2 plus 2 is divisible by 4. Yeah, so let's start. We've got k plus 2 times k plus 2 plus 2 is k plus 2 times k plus 4. Yes. Now, we're going to replace, remember we need the assumption. Our assumption is that k bracket k plus 2 is 4p. I suppose we can replace k plus 2 with 4p on k. You okay with that? Which is 4p on k bracket k plus 4. Don't know if I like having this on using the assumption. Oh, because k plus 2 is 4p on k. I'll just do it here. Because k bracket k plus 2 is 4p, so therefore k plus 2 is 4p on k. Now, if you expand, what have you got? You've got 4p times k on k plus 16p on k. 4p plus 16p on k. Actually, I don't know if I really want to. You know what? I don't want to do that. I want to keep those k's on the bottom. Why don't I just bring out the 4? Why don't I just do that? 4. Don't those p plus p on k. Because these k's cancel, don't they? Yeah, that's divisible by 4 because k is just a number, p is just a number. But look, it's 4 times something. I don't know what they've got.
Thank you.
Just to change here, if you can expand this as k squared plus 4k plus 2k plus 8, and then I just want to rearrange and get k squared plus 2k plus 4k plus 8, and then I'm going to replace the k squared plus 2k up here with 4p, which is 4p plus 4k, this is much better, plus 8, using the assumption, alright, which is 4 lots of p plus k plus 2, which equals 4 times q, where p plus k plus 2 is an integer. Please, this is much better. And, okay, therefore divisible by 4. And your conclusion. Girls, do not do that other way because of the fraction bits. You really don't want to be putting fractions. I just would be very careful. You don't know what values you're going to get. So you need to go for another approach. Yeah, it needs to be single line. All right. So, and then can you do your conclusion? Girls, you can do all the questions now in that exercise except for the ones with the inequalities. So I think all the way up to question, you can do all the way up to question 20. Okay.